Okay, so in this video, I'm going to prove our last application of the monotone convergence theorem. And in fact, the last result that we'll discuss from chapter 4. So, of course, you should add everything in this video to your notes. All right, so what does the corollary say? It says that if you begin with any sequence g sub n of non-negative measurable functions, then, well, first of all, the sum of the series of these functions is going to be defined non-negative measurable, as we'll point out later in the proof, and the integral of the sum is equal to the sum of the integrals. So we can interchange the integral and the infinite sum whenever we're dealing with any sequence of non-negative measurable functions. Okay, so let's do the proof. And we'll see that this is a fairly straightforward application of the monotone convergence theorem. All right, so for each positive integer n, we're going to let S sub capital N be the capital Nth partial sum of the functions g sub k. Right, well, then, because each of these g sub k's is non-negative and measurable, each S sub capital N is going to be non-negative and measurable. Certainly sums, finite sums of non-negative measurable functions will be non-negative and measurable. And furthermore, this sequence of partial sums is increasing. Why is it increasing? Well, because each g sub n is greater than or equal to 0. So, writing that, we have, just move up a little bit. So it's increasing, as we said, because each g sub k is greater than or equal to 0. If you want, you can check that. All right, well, what else is true? Well, the limit of our sequence of partial sums, S sub n of x, is equal, by definition, the sum of the series. Right, that's just by the definition of what we mean by the sum of the series, and because, as we said, these S sub capital N's are increasing, we know that the limit is necessarily defined in the extended reals. So this is just straight from the definition of what we mean by the sum of the series, and we might note, well, this sum of the series might actually equal plus infinity. So this series could diverge, but that's okay. The point is that the limit is necessarily defined for each x in x, because we have an increasing sequence, and we know that when the limit of a sequence of non-negative measurable functions exists, it too is going to be non-negative and measurable. All right, maybe we could even add that statement there, that this is going to belong to the collection of non-negative measurable functions. All right, well, we have everything that we need now to apply the monotone convergence theorem. So, by the MCT, what can we say? The integral of the sum of these g sub k's. Well, that, as we said, is equal to the integral of the limit of this sequence of increasing measurable functions. Whenever we have an increasing sequence of non-negative measurable functions, the monotone convergence theorem says that the integral of the limit is equal to the limit of the sequence of integrals. All right. So what is that? Now, this is equal to limit for capital N of the integral. Well, what was S sub capital N? Well, it was just our capital nth partial sum of our g sub k's. So that looks like this. But we know that the integral is linear with respect to non-negative measurable functions. So because what we have is a finite sum here, we can interchange this finite sum in the integral. And we write it like this. All right, and now, lastly, let's note that each of these integrals of non-negative measurable functions is greater than or equal to 0. So that means that our associated sequence of partial sums here is necessarily going to be increasing, right? As our capital N's increase, so does our sequence of partial sums, and that means that this limit actually is defined. Well, we know that in general. Whenever we have a series of non-negative extended real numbers, the sum of the series is defined, and by definition, the sum of the series is equal to the limit of the associated sequence of finite partial sums. So this limit here is, in fact, just by definition, the sum, as k goes from 1 through infinity, of this series here. All right, and that is all that we need. We've shown that the integral of the series is equal to the series of the integrals as needed.